Okay, so I wanted to finish up what we didn't cover on Friday in class before we have our inverted lecture on Monday. So I'm going to go through those slides so that you can look at those this weekend. And then I'm going to open up the slides for the next set of Chapter 11 and go through those fairly quickly, but just give you some details here and there that you might need to know so you can watch that before the inverted lecture on Monday. And so we started talking about the fact that you can actually take alcohols and react them with these sulfonyl chlorides. For example, here's methane sulfonyl chloride. Also, we talked about tosyl chloride and the triflate version in the presence of a mild base. And we can make, in this case, the mesylate, but also recall we can make tosylates and triflates. And now we've got a good leaving group. Notice we've retained the stereochemistry of the alcohol. So the stereochemistry that we have here in our starting alcohol is preserved in this product. Now we have a good leaving group. We now have a strong nucleophile that can come in, do an SN2 reaction, force the leaving group to leave, and end up with inversion of stereochemistry. And so this is a great way to do these stereoselective type reactions or stereospecific reactions where we're starting off with one stereochemistry and we're getting exclusively the inversion of that stereochemistry in the product. Ethers can be synthesized in a variety of ways. We've already talked about the ether synthesis using the Williamson ether process. But you can also make ethers using ethanol and sulfuric acid. So for example, if you take ethanol and you add sulfuric acid to it, you can get diethyl ether if you keep the temperature low. But of course, you'll get elimination if you increase the temperature to just under 200 degrees. So at lower temperatures, heating a mixture of ethanol with sulfuric acid, you can get diethyl ether. And actually, this was this process has been known for a very, very long time. And this was what was at one time called oil of vitriol, was what diethyl ether was known as, because sulfuric acid is known as vitriolic acid in the old days, or vitriol. And so if you take ethanol, sulfuric acid, you can get diethyl ether. Now the mechanism for that is, of course, the alcohol gets protonated by the sulfuric acid. You don't have a full equivalent of sulfuric acid present. It's just a catalytic amount. And then another alcohol can function as a nucleophile and displace water, and you can end up making diethyl ether very, very efficiently. We'll talk about the mechanism on Monday before the inverted lecture, but during the inverted lecture, excuse me, but you can think about this before you come to class on Monday. Now let's look at this reaction. So we're going to take tert-butanol and methanol, and we're going to treat those with sulfuric acid. So it's a mixture. And the first thing that happens is we're going to protonate the tert-butanol. Of course, you'll also protonate the methanol, but nothing can happen there because, whoops, I don't know what happened here. Sorry, there should be a 2. This, of course, is OH2. So this is protonated alcohol. You've got the water leaving group. There it is, correct. I don't know why it didn't show up. The rate determining step, the water leaves, you end up with the tertiary carbocation. Rate determining step, of course, and now methanol can come in, react with the carbocation. You end up again with the protonated species, which is the protonated ether at this case. And then, of course, more alcohol or the bisulfate can come in and deprotonate, and you end up generating the ether. We've already talked about the Williamson ether synthesis, so I'm not going to spend too much time there with that. Some examples. Of course, you could take tert-butoxide, methyl bromide, and end up making methyl tert-butyl ether. This process works okay, even though this is bulky, because there's no way you can do elimination on methyl bromide. Doing the chemistry this way is really not particularly favorable, right? Because we've got a good base. It is a pretty good nucleophile, but this is not a good electrophile, at least for SN2 type chemistry, and so this actually ends up doing an elimination. And so you don't get that chemistry occurring. We can actually use tert-butyl ethers as protecting groups of alcohols. A protecting group is a group that we add to mask the properties of a particular functional group during a reaction. And we might want to do that because it could interfere with another reaction we want to do. But it's important that a protecting group can be something that is easy to put on, but also easy to take off. Okay? And since alcohols with that OH group are acidic, a lot of times we have to protect them to remove that acidity temporarily, because we might be wanting to use some type of nucleophile that's also a strong base. And the easiest way to protect alcohols is to convert them into tert-butyl ethers. So you can take the alcohol, isobutylene, sulfuric acid. Of course, the sulfuric acid protonates the isobutylene. You end up with a tertiary carbocation. The alcohol then attacks that tertiary carbocation, and you end up making a protected alcohol, which is a T-butyl ether. Notice there's no hydrogen on the oxygen at this point, so it's no longer acidic. You can do the chemistry that you want, and then you're good. Now, how do you get the alcohol back? Because a protecting group has to also come off and give you your starting functional group that you wanted. Well, we know that this process is reversible. And so we can just add water and sulfuric acid to this, and we can actually get back to the alcohol pretty easily just by reversing the reaction. So let's look at an example. If we wanted to do this reaction where we were going to take this alkanide, where we have the carbon with the triple bond, right? Negative charge on the carbon. This should function as a pretty good nucleophile and displace the bromide on this carbon in an SN2 type reaction and form a new carbon-carbon bond that you see over here. Unfortunately, the pKa of these is around 25, and so before this can function as a nucleophile, it's going to function as a base. And here we have an acidic proton with a pKa somewhere around 16. And so what happens is, if you were to mix these two things together, you would get no SN2 chemistry, you would get all acid-base chemistry. It's very important that you recognize that your acid-base chemistry, with protic acids and strong bases, almost always occurs before you have any chemistry occurring as an SN2 type process. Okay? And so what would happen in this reaction is you would actually form acetylene, which is a gas, and you would form the sodium salt of the alcohol and not get exactly what you wanted. Okay, but there are ways around that, and we'll talk more about that on Monday. Now, this is the last bit of Chapter 11. You need to go through these slides and go through this part of the book before class on Monday. But I'm just going to hit some of the highlights. So I want to go through this fairly quickly just to give you kind of a supplement that you might need for the pencast that you also need to view. So we all know that ethers have an oxygen atom, lone pairs, they can function as bases. And so it turns out that you can take ethers and treat them with strong acids like HBr or HI, even HCl for that matter, but particularly the bromide and the iodide, HX. And you can actually convert ethers into alkyl halides and spit out a molecule of water. Okay, so for example, if you take ethyl methyl ether, treat it with HBr, you get methyl bromide and ethyl bromide as products. Okay, so really you need two equivalents. This isn't a balanced equation. You need 2 moles of HBr. One of the things, as you've probably recognized, is organic chemists are quite bad about balancing equations sometimes. You could take tert-butyl methyl ether, treat it with HI, or you could also use HBr, but here's the example of HI, and you could get alkyl iodides pretty easily here as well. And again, we're losing a molecule of water. The way that this happens in this particular example, if we look at this, The tert-butyl methyl ether gets protonated by HI. HI, of course, is a strong acid. We end up with a protonated ether. This now is a pretty decent leaving group, and so it can leave, generating a tertiary carbocation. Iodide, of course, is in solution since we're using HI, a good nucleophile, and this attacks, and you end up with the tert-butyl iodide. Okay, so the part of generating the tert-butyl iodide in this reaction occurs by an SN1 mechanism. However, we had the methanol leave as a leaving group, and it's still in solution. And so what happens is the methanol will also get protonated by hydrogen iodide to give the protonated alcohol, and now we have water as a good leaving group. And now through an SN2 mechanism, the iodide can come in, displace the water leaving group, and give me the methyl iodide. And so that's how you end up getting the two alkyl iodides out of this particular reaction and a molecule of water. And so this is a perfect example of where one molecule is actually undergoing two different mechanism types, SN1 and SN2, to give the products that you see. So I will not discuss that one here. We won't go through the concepts tests. Epoxides, of course, are a special ether because you have the ring strain in the three-membered ring. And we know that typically alkoxides, CO- are bad leaving groups, but that's not the case in epoxides because of the ring strain. So nucleophiles can actually attack the carbon of the epoxide and break one of the carbon-oxygen bonds, and so you can form a new carbon nucleophile bond and you get a new alkoxide in the process that's the leaving group. And this is all driven by ring strain. So for example, if you look at the case where you have this symmetrical epoxide, if you look down this plane, you can see that both sides are identical. So it doesn't matter which carbon gets attacked. Cyanide can attack one of these carbons. In this case, they have it going to this carbon. So you can see the cyanide coming in, attacking, breaking that weak carbon-oxygen bond. And then upon workup, the alkoxide picks up a proton from water. And so you can form these so-called cyanohydrins because of the nucleophilic addition. You can also do this type of chemistry with strong acids. Of course, the strong acid will protonate the oxygen of the epoxide. The chloride can then function as a nucleophile, and you can open up to make these chlorohydrins. And notice the stereochemistry here is trans. Now, when we are under basic conditions, that is, when the nucleophile is in the negatively charged state. So, for example, we're dealing with this S- nucleophile here, this thiolate. In this particular case, we have an unsymmetrical ether. And so we have a carbon which is more substituted because of these two methyl groups, and we have a carbon that is less substituted because of these two hydrogens. And it turns out that under basic conditions, when no acid is present, the nucleophile prefers to attack the less hindered, less substituted carbon. And that breaks open the ring, and you end up forming the new carbon-sulfur bond. You have the new alkoxide. Then when you treat it with water, of course, the alkoxide picks up a hydrogen from the water, and you end up with your product. Okay? So when we have an unsymmetrical epoxide, where one carbon is more substituted than the other, and we're under basic conditions, the nucleophile will attack the least substituted carbon. However, under acidic conditions, that's not true. Under acidic conditions, the nucleophile will attack the most substituted carbon. Okay? So let me see if I've got an example here. Yes, so if we look at 1,1-dimethyl oxirane, oxirane is another name for epoxide. The first step, just like with an ether or an alcohol in a strong acid, you're going to protonate that oxygen. Now we have a protonated oxygen. Oxygen bears a formal positive charge. And it turns out that this is no longer the triangle as shown, really. This bond is actually weaker. because this is the oxygen-carbon bond to the most substituted carbon. And so this weaker bond can happen because this carbon can take on a partial positive charge, as you see here in the transition state. And so now the nucleophile prefers to attack the most substituted carbon because that's where the weakest carbon-oxygen bond is. So under acidic conditions, the nucleophile always attacks the most substituted carbon of the oxirane. So you need to keep that in mind. Okay. So here's an example where you're taking our unsymmetrical epoxide. Under the top conditions, what you'll see is in step 1, it's methoxide. So this is clearly under basic conditions. So the alkoxide will attack the least substituted carbon, and you'll end up with this product after workup. Here, however, we are using methanol as the solvent, and we're using sulfuric acid. So we're clearly under acidic conditions. So what happens is the sulfuric acid protonates the oxygen. That makes this carbon-oxygen bond weaker, and so now the nucleophile will attack at the most substituted carbon and give us this product. So that's kind of cool. We can pick where our nucleophile goes by choosing what types of conditions we are using. I'll let you look at this, but basically the take-home message here is that this has actually been used, this type of chemistry has been used to do a variety of chemistries that are important. So if you have ever taken Ceravent, this molecule is actually made by a ring opening of an epoxide. Here we've got a nucleophile. This is clearly in the absence of acid, so the nucleophile will attack the least substituted carbon, forming the new carbon-nitrogen bond here, and then going through some steps to convert this molecule into the drug. Epoxidation, how do we form epoxides? Well, there's several ways that we can form epoxides, but one of them is through the use of what are called peroxy acids. And my favorite peroxy acid is called MCPBA, or metachloroperoxybenzoic acid. But basically the chemistry is the same for all of the peroxy acids. So if you look at this, it kind of looks like a carboxylic acid with one additional oxygen. So instead of a C double bond O, OH, we have a C double bond O, O, OH. And these are very good oxidants that can actually form epoxides very easily. So if you take an alkene and you mix it with a peroxy acid, usually in a solvent like dichloromethane, you can get epoxides very, very cleanly. And it's actually this oxygen atom of the peroxy acid that is delivered in the epoxidation reaction. We'll talk a little bit about the mechanism, but I'm not terribly concerned that you know the mechanism of this particular reaction in high detail. But the important thing to note is that notice that the methyl groups in the epoxide are cis to one another, and also notice here in the product they are cis to one another, which suggests that this reaction actually occurs in a concerted fashion where the oxygen bonds between the two carbons, where the oxygen being bound to the two carbons, I should say, is all happening at the same time. Also notice if we take the trans stereochemistry of the alkene, the methyl groups will be in the trans configuration with respect. And it's 100%. So if you have 100% trans 2-butene, you're going to get 100% trans dimethyl oxirane. If you have this 100% the cis 2-butene, it's going to be 100% the cis dimethyl oxirane. Now again, I told you that the mechanism here I'm not extremely concerned that you know in detail. It's actually a fairly complicated mechanism, and basically what we believe happens is that you form some type of what's called a pi complex, because that oxygen atom is actually electron deficient, and in doing so you can actually push the arrows this way, kind of complicated. So think of it as one carbon-oxygen bond is being formed, so is the other. And you can end up forming the product. So go through these on your own. I also want to talk just a minute about phase transfer catalysis. Let's suppose you want to conduct this reaction where you take this alkyl halide and you react it with sodium cyanide to make this nitrile. A simple SN2 reaction. We've got a good nucleophile, we've got a fairly decent leaving group, it's secondary, it can do SN2. And so on paper anyway, it looks like this reaction should be able to work. The problem is that we know that alkyl halides are soluble in organic solvents, but not water. And we also know that sodium salts of things like sodium cyanide are soluble in water, but not organic solvents. So getting these things to actually mix to where they can react is actually a problem. Because if I take water and the alkyl halide and I mix them together, I just get two phases. And no chemistry can occur. You've got to have intimate mixing of all the components. Well, phase transfer catalysis allows us a way in which we can actually transport a nucleophile from an aqueous phase and transport it into an organic phase. And so basically what we're going to do is we're going to exchange the sodium cation for a cation that's actually organic soluble through a process similar here. So if you think of this, here's a flask. We've got our sodium cyanide in the water phase. We've got a boundary, and we've got our organic phase, for example, methylene chloride containing our alkyl halide. Cyanide can't get into the organic phase because it's water soluble. But what we can do is add another salt, and here we've abbreviated it as Q plus X minus, and Q can be something like a quaternary ammonium salt. So imagine a nitrogen atom with 4 R groups attached to it. It would have a positive charge. It would be positively charged just like sodium is positively charged. Except that nitrogen now has all these R groups around it that are organic. So you can imagine, let's say we made those R groups 5 carbons long. So we'd have these 5 carbon chains. So we'd have 20 carbons attached around this nitrogen. Well, that all of a sudden makes that very organic soluble. And this salt could actually be dissolved both in water because it's a salt, but it can also be dissolved in the organic phase. And so what happens, since this salt, or this so-called phase transfer catalyst, can actually move between the phases, when it's in the water phase, sometimes the sodium and the Q plus get exchanged out and you make Q cyanide, if you will. Well, now this is will be soluble in the organic phase. And so this will migrate into the organic phase where the cyanide can actually react. And this is a process that's catalytic. You don't need a lot of this so-called phase transfer catalyst. Now, I'm very fond of phase transfer catalysis. I'll talk more about that on Monday, primarily because this process was developed in my home state of Oklahoma. So it's kind of a home pride kind of thing. We'll talk more about it. But this is how you would actually conduct some of these reactions that we've been talking about. Okay, I'm going to stop there and get this posted to YouTube for you.